No, a set of points that are all equidistant to a center point. Okay, so the reason that it's defined like that is because as you guys get into Algebra 2, you're going to talk about things that are called conic sections. Conic sections are circles, parabolas, ellipses, and hyperbolas. Circles, parabolas that go, up like a cup, down like a frown, quadratics. You guys have seen those. A hyperbola are two parabolas going in opposite directions, either vertically or horizontally. And then an ellipse are two parabolas that are joined together that have the same shapes. And there's rules about this whole idea of the center point about things being equidistant of what defines them. So this is the conic definition-ish, if you will, of it, all right? You guys all know that. As you start to sit there and start talking about I try. Circles are labeled by their center. There's a symbol for circle because writing the word circle takes too long. It's very difficult. That means circle A. Not like literally circle the letter A, but it's circle A. A would be the point at the center. That's how these are defined. They're defined by their center. So if you drew that, A would be in the middle. Okay? Just like you'd have segment AB, endpoints of a segment with point A, point B. Line AB goes through points A and B, and so on and so on. So you have circle A. Now there's other definitions that you guys have all seen. For example, the first one, radius. What's a radius?
The radius is
from the center to the side, yeah. The radius of a circle is a segment from the center to the side of a circle. All right, the radius is going to be the segment from the center to the side of the circle. The radius is what defines a circle. That radius never changes the entire way around the circle. That's what makes it equidistant to the sides. An oval is what's called an ellipse, and you can get into all these different things. Yeah. I'm trying to get it close-ish. Yeah, I'll get over it. All right. Chord. Bless you. Chord in a circle is something you've probably never heard of before. What do you got?
Is it like from the side to the side that doesn't make a circle? In the center?
Yeah, exactly. Well, if it goes to the center, it's just a fancy chord. A chord is the segment that goes from one end of a circle to the other edge. So it's a segment with endpoints on the circle. So C, B. Chords go from one edge of a circle to the other edge. And there's an infinite amount of chords that can be drawn. The reason why we define the word chord before we define the word diameter is because a diameter is a chord. It just goes through the center. The diameter of a circle has endpoints on the circle, but it goes through the center of it. So it's the fancy chord. So your diameter is a fancy chord that goes through the center. The diameter of a circle, since it goes through the center, cuts the circle into two equal parts. Those two equal parts are called?
That word, the one that's
Nope. Semicircles. I just about to say the word. A diameter cuts a circle into two equal parts called semicircles. And that comes up a little bit later on. I wouldn't worry about that quite yet. So your diameter cuts the circle in half. It goes through the center. What is the diameter made up of? Two radius. Very good. The diameter is equal to, and we usually use the letter D, two radius. Oh, speaking of radii, plural radius. You okay with that? So, what do you know about all the radii in a circle? They're all the same. Just in case you forgot that, the radius, every single radius of a circle is congruent. All radii are congruent. All radii congruent in a circle. Okay. All radii will be congruent within a circle. This is plural. The last two are different. The last two are definitely ones that I know you've never seen. Secant and tangent are both trigonometric functions. We know tangent being opposite over, yeah, trigonometric is a word. You know sine, cosine, tangent, right? Those are trigonometric functions. T-H-A-T-W-O-R-D. Trig functions are sine, cosine, tangent, and their inverses. Cosecant, secant, and cotangent. These have nothing to do with trigonometry right now. They're just another term that they use within circles. A secant, think of Metallica, the song, Seek and Destroy. Secant, Metallica?
Do they not know? You guys don't know that?
Seriously?
Yeah, you guys know that. Yes.
Want to eat something.
Go to the store.
Anyway, a secant. A secant is a line through a circle. So I think of it as like an arrow that goes through the circle, so it destroys, so it's seek and destroys it. And it what's that?
Arrow through an apple.
Right. Seek and destroy. Anyway. So a secant is a line that goes through a circle.
Does it matter if it goes through the center?
Nope, not at all. It does not matter if it goes through the circle. What matters is that it touches the circle in two spots.
You said
Oh, I meant the center.
you don't like it.
It touches the circle in two spots.
Stop.
Tangent.
He's just like. Yeah, why do you insist on
How,
moving everything?
excuse me, how many places does it touch the circle then? You're right.
I know. Wait, it's like this.
You're right. But how many places does it touch the circle?
I don't know. Research. Caroline, what are you doing?
Tangent
She thought. Oh, I was gonna.
is, it could be, this could be a line, a segment, or a ray. Let me move this up here. That touches the circle at exactly one spot. And you're right with the idea that it touches it at one spot and becomes perpendicular, because no matter where you touch a circle, if you touch it at one spot, what can you always draw to that one spot? You can always draw a radius to it. So no matter what, anytime you touch a circle at one spot, you can always put a radius drawn to that spot that would always be perpendicular. Yes, ma'am?
I thought it was two because like the line on the other side.
That's a secant. All right. There are things that you're gonna see. You're gonna see all these stuff combined together eventually. But for right now, I just wanted to define that a tangent touches once because it can make a T. The secant goes through it because it wants to seek and destroy it, because that's you shoot an arrow through something. It's the dumbest way to remember it, but it works. Believe me, I could think of something dumber. Probably. Yeah, I don't want to, but you know. So the tangent touches it at exactly one spot. So let's see here. I got to draw my secant in. Where am I at? E, F, G, H. And then if I want to draw a tangent, see how it'll be a tangent here. A tangent if you look at the diagram here, because I'm running out of space in this larger one, if I draw a tangent, if I call this line IJ, guys, in that diagram here or over here, whichever one's easier to see, I can say that line IJ is tangent to circle A at point B. What that means is that you've got a circle, circle A. There's a line that's tangent to it that creates a radius, AB, and is perpendicular at B. That's the kind of information that we're going to be looking at today. Okay? Yes, ma'am?
So wait, tangents are radius?
Tangents aren't radius, they're perpendicular to a radius. So a tangent segment is perpendicular to a radius. Okay? Let's see if I can draw this again here. If I touch the circle at one spot, I can draw a radius from there to that spot, and it'll always be perpendicular. No matter where that goes. As you rotate that all the way around, as that tangent segment comes up all the way around the circle, no matter where it is, you can always draw a radius because you can draw infinite degrees of radius. Okay, so you can always find a spot that's perpendicular. What's wrong? You give me the cross eye.
So it's on the outside of the circle?
Yeah, it touches the outside. Yep, it touches the outside. Yes, ma'am. What are you going to have to do with it? Well, I'm getting there. I'm getting there. Because what happens now is that we can take stuff that we've done before and just add a circle to our diagrams. For example, if I go back to drawing an angle bisector. If you have an angle bisector, if you guys remember this from way back when, if you put any point on that angle bisector, we always said that it was equidistant and perpendicular to the sides. Remember that? The reason that we could have done that was because you had right angles, you had the equidistance to the sides, and you had a reflexive part here. You had two congruent triangles, right angle, a hypotenuse, and a length. So you had you had hypotenuse leg here. Whenever you were on that angle bisector, you could do that. Which then meant, because of corresponding parts, these outer pieces were the same. You vaguely remember that? It wasn't that long ago. Well, here's what changes for today. We take this exact same diagram, we put a circle in it. And when we do that, those two segments from the outside, they're no longer an angle, they're common tangents. They start at the same spot. They're perpendicular to a circle. They're perpendicular to a radius, which means they're the same distance from the starting point. It's just adding a circle to a diagram that we have done before. Okay? So what happens here is that if two tangents share common start, trying to think of an easy way to write this out. If you have two tangents that start from the same spot and they're touching the same circle, they have to be the same length. Because it boils back down to being, if they touch a circle, they're perpendicular to a radius. That radius is the same whether or not you're on either side of the circle. Thank you. That reflexive side coming from the center of the angle, if you will, to the center of the circle, it's still reflexive. So by using that whole idea of the corresponding part stuff, you get these lengths on the outside being the same. So when you have what are called common tangents, they share what's called the same point of tangency. Actually, I'm sorry, that's not the point. The point is where they run in the circle. But if they share that same starting point, those two segments are going to be the same. Which means, just like we did before, you're going to have 1- and 2-step algebra problems to solve for x. And the only difference between what we have done before and what this diagram looks like is they put a circle in it. That's it. Okay? That's really it. What's wrong, Tope? It's like you don't believe me. You don't believe me? You're thinking about stuff. For example, can I put an example up here? Or you guys need a second to draw that? Let me get a drink of water.
You're making weird noises again.
Oh,
So this is,
that's you talking about with the ice cream thing.
you said the making weird noise.
It'll tell you in the descriptions of this style of a problem that it'll say JK and JM are both tangent to circle L. They tell you that, yes ma'am? Yeah. A lot of just basic definition and diagram stuff. Nothing, not too much algebra for that. Okay. Which means that they tell you that these two run into the circle. You can draw this in, and you get your reflexive. You have hypotenuse leg for both of them. which means that these two, oops, have to be the same. So basically, algebraically, all you have to do is 3x equals x plus 12. Since they share that same external starting point, and they're both tangent to the beginning, or they're both tangent from that starting point to the same circle, they have to be the same length. Yes, ma'am?
Where's your, like, you have 1, 3, and then.
I originally had 2 here, but I made it 3 because it was on the circle side. All right. So algebraically, you just get 3x is x plus 12. What do you do? Subtract the x. Oops. And what's x? Okay. One thing I will suggest that you do, especially a lot with circles, always verify that it works. We know that those two segments have to be the same. What's 3 times 6?
18.
What's 6 plus 12? Does 18 equal 18?
Theoretically.
Theoretically, yes. So should we say that we did this correctly?
Theoretically.
Theoretically, yeah. This is the kind of stuff we're heading towards, okay? We're going to see a lot of factoring, a lot of foiling, and it's just the same basic idea of it's a generic setup for these things, but we're going to keep going. What I have for you guys tonight is basically looking at diagrams like this and identifying what parts are what. And I have something that I want you to draw, what are called common tangents. We'll get into more and more of the algebra of it tomorrow. I gotta remember what page it was. I had forgot I had posted it yet. It is 655. Do those, please. What I'll do, I did this earlier and it worked out well. On you guys' way out, if you want to come up now, just take a picture of the page. Use your phone, just take a picture of it so you don't have to worry about trying to figure it all out. Okay. We'll build out of this more tomorrow, do a lot more of the algebra. There's a couple more diagrams, things I didn't get a chance to show you, but we'll go from there.